Hey everybody, this is Larry. This is day 15, halfway through the May Leetcode challenge. Let's get started. Maximum sum circle subarray. Okay, hit the like button, hit the subscribe button, all that stuff. Given a circular array C of integers represented by A, find the maximum possible sum of a non-empty subarray of C. Here, a circular array means the end of the array connects to the beginning of the array. Formally, a sub I is equal to a sub I when 0 is from a to dot length and so forth. Also, a subarray may only include each element of the fixed buffer A at most once. That makes sense, so you can't go in an infinite loop. Okay. So I think for me, I would start doing this problem by breaking it down into the number of cases that could happen. So I'm going to do some ASCII art here. So let's say I have some array like A, B, C, or just A sub I sub plus 1, A sub I plus 2, dot, 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 A sub n. I guess this is actually A sub 0, but, and this is A sub n minus 1. Okay, fine. But so the way that I would think about it is, well, one scenario is to use the entire array, which makes sense, obvious. Another scenario is, maybe let's list them out, use entire array. Another scenario is, well, use a subarray. And in these cases, we can do contains algorithm. This is I wouldn't say it's a standard algorithm. It's actually a little bit tricky to learn for the first time, but it is something that comes up for whatever reason, happens a bit. And without the circular part, that is the standard answer on how to solve this. And you're doing a for loop, and it'll solve it in like 2 minutes, maybe, if you've already done it anyway. If you haven't, then it's a little bit tricky. And then now we have to address the circular part, right? The circular part is such that, okay, whoops. So you have an array. You can look at it like this with two array back to back because it's circular. And why did I choose two array and not more than two arrays? Well, because let's say we choose 3, and our maximum sum is here, spanning from left to right or something for whatever reason. Well, the answer is obviously you cannot do that because you can only hit each element once. And in that case, you use the entire array, and this would already be the case. And so yeah, so in this case, I would only need to look at the array times 2, or like, duplicated once. And then now looking at this case, what cases are there? Well, there's really, all the other cases are in here, meaning if it doesn't intersect, then it's not interesting in that it's already addressed in the contains algorithm. The only place where it's interesting is if it starts from the left side and it ends to the right side. And also we have to keep track of the fact that we don't use the same element once, right? So you cannot do like the last element and then use the entire array. Or, okay, maybe that's more obvious because you cannot use this entire subarray, but you cannot do, I don't know, I missed the dot, dot, dots. So the numbering looks confusing. But you cannot do like, I don't know, a sub I plus 2 and then all the way to a sub I plus 2 again, right? One is that I don't think that can happen. Can that happen? My intuition is that, and I haven't been able to prove it yet, but it can happen because for that to be the maximal sum, like let's say we take this, right? For this to be the maximal sum, which means it takes the entire array, that means that this sum from, in that case, we span it like this. Let me draw some ASCII arrows. Let's say start is here, and n is a lot of space bars later. Space bars lagging. And the n is here. Well, that means that we basically, if you rewritten it, if you rewrite this, you get this sum, something like that, right? Dot, all the way to a sub 0 plus dot, dot, dot plus a sub I plus 1. Oh, put this in the wrong place, but right. And in that case, this is just equivalent to, you could really easily rewrite this to just oops. You could rewrite this to this, which is this is equal to just using the entire subarray, right? So in that case, like you don't have to handle that case of it wrapping around. Or I mean, you may have to handle it, but in that case, you would just use this entire array anyway. So now the only case that's remaining is if it ends or if it begins at near the end and it ends near the beginning. So we can, so we can actually, in that sense, we have to maybe keep track of a little bit. But what I'm thinking now is we just use Cadane's algorithm on the array times 2, but we do a little bit of tracking to make sure that we don't go over the maximum n. And I think that's all there is. In a sense, we could use Cadane's algorithm. Another way to formulate this is that we could use Cadane's algorithm on the entire array, which is, that's true without the circular part. And then you could kind of, in a way, in a greedy way, maybe. Does that work? I mean, I think now we approved the case analysis, but what I'm trying to think about now is try to get it down to linear time, right? Because otherwise it's trivial. Well, if I start at here, how far can I get? And also, what subproblems can I get from I plus 1, right? Yeah, that's kind of the way that I'm thinking about it now. So let's say so and this I believe will this understanding takes a little bit of how to say it, understanding around Cadane's algorithm in general, and the fact that it builds up previous states, and then now we're trying to think how to use those previous states to get the result as well. Because they're O of n, and you cannot afford to do it O of n times. Or you can, then you just do it another way anyway. But yeah. And do we always want to be? I think for me, the hard part about this is trying to prove the greedy a little bit as well. Meaning that, let's say we go over. Well, as soon as we go over, we know that, is it just do we return the maximum sum or the index? Okay, just the maximum sum. So as soon as we go over, I think, yeah, okay, as soon as we found any place where we go over n, where n is the list of the initial array, then that means that we found one case where we use the entire array and then we don't have to go on. And then every step before that, we could use greedy. It's not quite greedy, it's dynamic programming. The same way that we use Cadane's, because we always want to take the current element or 0, whichever is better. Yeah, and we also have to maybe handle the case where if all the numbers are negative. Okay, so let's get started and then let's play around the texture ideas. I think we have enough to get something that maybe resembles a solution. So yeah, let's go A. Let's get an A2 array, which is A times 2. And what that does in Python, it just creates an array, just to show you a little bit. It just creates 2 copies of the array next to each other. Or I don't know if that's the precise way of saying it, but that's kind of what I'm doing in case. So sometimes I get Python questions. And then now we use Cadane's algorithm, right? So we have the result that we're returning. And actually, this is maybe negative infinity. Yes, negative infinity, because we have to handle the negative answer as well, and also at least one element. So now we have a current running prefix sum, and just the last index that we keep track of. So now let's just set it to -1 because this is before the beginning. And then now for index element, let's just use num in enumerate A2. Okay, so if okay, so now let's just do the running sum plus, and the thing that I'm thinking about just about all the edge cases, and it's a little bit tricky to get them all right. So I'm just thinking about it a little bit. So current plus is equal to the current number, right? And then now let's just do if current best is equal to the max of current best, because we always want to choose at least one number. Yeah, is that it? And then yeah, and then current is equal to max of 0 and current, so that we set it up for the next number next time. If it's because if it's less than 0, then you basically discard everything before that because it doesn't really matter. And then now, except for we have to maybe change something. So that's the usual Cadence algorithm, but let's change it so that if current is less than 0, or maybe even less than, yeah, I guess it doesn't really matter if it's the same. Then that's index is equal to the current index, right? And we have to do some modification about the stuff we said, actually, because in this case, we want to do this only if the current index minus last index is equal or is less than n. It could be off by 1, actually. Think about this for a second, because this is 0, so minus -1. So this is 1 for the first element. So okay, that's okay. Is it less than or equal to so that's the number of elements, and the number of elements can be at most n. So okay, something like that. And also, forgot about that part. Is this enough? Let's run it and see, I suppose. I mean, this is regular thing, so let's take a look. A lot of copy and pasting. Oh, actually, if it's bigger than n, we probably want it to be the entire array. And also just return already, maybe. So that maybe that's a little bit wrong. Cool. So, okay, so there is, okay, so there is an edge case that I was wrong about with this one, which I was worried about a little bit when I was thinking about it. And kind of, hopefully this will kind of, with these kind of problems, getting it right is cool and interesting, but I also want to focus on kind of how to do debugging. I feel like nowadays people are not doing as much debugging and self-debugging instead of just like pasting the code and be like, oh, what's wrong? But yeah, in this case, our original assumption was that we can use the entire array, but it may be that it's optimal to use less than the entire array, but because the entire array is positive, we kept on going, right? Oops. So definitely this is a case where our assumption was wrong. And then the question is, well, how do we deal with it? At this point, we know that index minus last index is greater than n. We just didn't do anything about it. I kind of alluded to it. So, well, now the question is, what do we want to do, right? If it's bigger than n, let's just take out the things that makes it bigger than n at the other side up until we get to n or less than n in a greedy way. Can we do that? So we definitely have to remove the 5, but then can we, I guess the invariant that we're trying to figure out if it exists is that how do we keep going on? I mean, in this case, the -3 is obvious because you could just, like negative numbers, you just keep on going. But what if there's a negative sum? Like instead of -3, there's like, 6, -9, right? Then it's kind of the same thing, but have, like if we're here, we're like, okay, yeah, obviously we have to dequeue the 5, but then we're here. Do we know to remove the 9, right? Well, 6 of the 9 so that we get 10. I mean, I know that there's a 6 coming as well, but in terms of subproblems, how do we do that, right? That's tricky. Oh yeah, and n is 30,000, but we weren't definitely going to do linear, so I don't think I would have thought about it any other way. And I think the constraints are here just to show you that the sum of all the numbers will fit in ints and not any other things. But so now we've shown that greedy-ish solution doesn't work. What is the second way about it? Well, how do we get the maximal of this subarray? Or maybe our assumption as well, which sometimes it happens. And I mean, I don't know, I feel like I always bring out that data structure, but in a way, do I do this? I guess so. In a way, okay. So now that we kind of think, well, now we ran into an issue, right? Oh no, what should we do? Now, sometimes it's worth doing, step back just a little bit, and that's, just to kind of think about what question are you asking. And, we had a strategy, we kind of play around with it. But then now I'm like, okay, at 5, what do I want to do? Well, I want to find the max suffix sum such that I want to find the, like, from here to here, the max sum suffix, right? Does that kind of make sense? In that going forward, you could say, like, instead of a prefix sum, you have a suffix sum of, okay, this is 5, oops, this is what, 5 plus, so -4, okay, maybe using dashes is a bad idea. And here, this is 2, yeah, 2 plus 2, say, and so forth, right? And then, well, you don't put a 5 because it overlaps. And then now we just have to take the maximum of those numbers, right? Well, in that case, now we just have now we just have a min q problem, right? And you could put this in a set. You could put these in different things. But and I'm gonna let's think about how I want to implement this. But then but yeah. And then for 6, just to kind of make it clear, for 6 we add it to the 5, but then we also just look at this suffix instead, right? It's sort of a rolling window, if you will, of possible sums. Yeah, I think that's how I would now attack this problem, which is easier said than done still. Um, hmm. Because now I'm just trying to think about the best way to represent this, right? So now let's just say we run through contains algorithm once. Let's actually reword this a little bit to, now we don't need all this other stuff. Let's just say now we have the traditional contains algorithm, something like this. And then now, what do we want? We want to construct the suffix sum in a way such that, yeah, and well, because we're doing suffix sum, we're actually, let's say, one element at a time. We're going from right to left, and how do we remove elements, or from left to right? So actually, it's one of those mono. Oh, geez. So in that sense, we're implementing a max stack, right? Because if you look at this as where this place as the bottom of the stack, and we process the number suffix. Well, here's a 5, here's a -9, here's a 6. Okay, right? And then when we pop, and then also the 5, I suppose. And then at the end, we want to pop them off as we process numbers to the right, and then getting the max inside that stack as we add it to the current sum, right? And in this case, it can actually even go negative, because it could be a negative plus a positive enough number that is the max, or at least like I wouldn't rule it out, because the alternative of this being negative is that we do what we did in the contains algorithm, but when we do contains algorithm, we restart the subarray or segment from here. But then in that case, you never want to go back here, right? So how did that happen? So in that sense, we already solved that problem of starting from here. With contains algorithm. So we only, even with negative numbers, we keep going. Okay, cool. So now let's do it that way. It's a fun Q problem. I don't think I've seen this problem yet, or I think people have asked about it, but I just haven't. I don't know. It just didn't come up. So cool. So now let's start with a stack. Let's go from right to left for num in A. So this is going from right to left. And we want to so what we put in the stack, to be clear, is not the number, but it is the running sum. So for that, I have to make sure that the number that we're popping is, like when we get to pop 6, for example, we have to make sure that we pop 6 and not whatever on top by accident or something like that. So I just need to be a little bit careful. Okay, so now let's just do a current sum is 0, 0. So current plus equals to num, and then now this current number is what we put on the stack. And I'm just trying to think about how to put that on the stack, maybe. Maybe I could use index. Okay, let's just use the index. Understand it's a little bit easier, but then now we have to do this in a little funkier way. Okay. And then now, as a normal thing, so what is the invariant? So invariant is, okay, well, while the stack length is greater than 0, and we want to only push when we're on, if it's bigger than the current max, right? So now, and the stack of the top of the stack is smaller than the current number, right? Because if it's smaller than the current number, then you put it on the stack. No, wait, if it's bigger than the current number, would you? No, wait, no, this doesn't make sense. I think I'm thinking of mine. He was got a little confused, but no. So if the stack is bigger than 0, and the top of the stack is smaller than your current number, then we put it on the stack. Right? Because what it is saying is that when you pop, you get smaller, right? So okay, so that's how I would process this. And then now we have to go through the second array, if you will. So now again for index num in array A. So first of all, we want to pop off a sub index of the stack. So okay. So now while length of stack is greater than 0, so it should always be greater than 0 because you never pop everything. And stack of -1, or the index of it is less than or equal to index, so it should only be equal to. Then stack, you just pop the stack. And then now we just have to get the max of the stack. I have to do a current again. Current is 0, 0. Current includes the current number. And it may so be that, like, given 5, maybe the top of the stack is all the way through, and that's okay. Well, all the way through minus the 5, so all the way through to 6, right? So then now best is equal to the max of best current plus the stack, the top of the stack, because that's the max stack result. And I think that's, well, let's see. I think that's roughly right. Maybe I have an off by 1. Oh, I didn't know that enumerate is not reversible. That's a little bit odd, but we could just make it into a list. Make it explicit, that's fine. I mean, what it's saying is that it takes a performance hit. Yeah. Can I get this backwards? There should be at least one thing on the stack, right? Let's let's point out the stack for science. Stack is empty, but that doesn't make sense. Oh, I think I converted it wrong. It's if stack is equal to 0 or thing, so okay. Oops. Oopsie daisies. Okay. Still out range, really? Because the invariant should be that the stack should have at least one element, because you can only pop off the beginning, but you get 2, 1. I don't know what this means. And also, there's a only if stack is greater than 0. Well, I guess it's top. That doesn't make sense though, because indexes. Okay, let's focus on one problem so that let me also put it somewhere else so that I don't lose the input. Okay, so we confirm that this is the test case that's giving us issue. Let's so 2 pops up everything except for the 3, and then 3 pops up everything. 0, 1, 2, 3. That sounds right, but I guess we just left off the last element, because the last element, I guess that makes sense. Because if, in this case, if we look at the last element, you only want the entire array, which we already calculated for, so that should be okay. Sometimes you get a little bit lazy thinking about the bounds, and that's what happens. Okay. Let me copy back my test case that I had put in the text pad. Notepad Emacs. Okay, this looks okay. So now let's give it a go. Actually, let's have some empty cases and stuff like that. Can it be 0 elements? No, at least 1 element. Okay. Did we try this one? It's a lot of general cases. Random cases. I don't know if they're general enough, to be honest, but looks okay. So pass the smell test for me. Let's see how it goes. Cool, accepted. So yeah, so I think so. First of all, apologies if this feels like a really long video, and it is, but that's fine. I think what I want to show is that sometimes you go with your hunch, and then but it's important to figure out how to debug your code, and I did run into some issues and some assumptions that I was close, but not quite right around the things. And then how I deconstruct this problem again, because I took a couple of minutes back to just be like, okay. You see it live, but I was just like, okay, what is the question that I'm asking? And that for each one here, for the second array, I'm asking myself, okay, what is the biggest suffix sum that goes through that array? And then I was like, okay, well, suffix sum, we know how to do suffix sum. That's just the inverse of the prefix Cadena algorithm that we did, right? We just kind of run it backwards. But instead of throwing away and getting the max, we store each of these numbers in a way such that when we move 1, we get all of 1 time, right? So I hope that the debugging helped, and the kind of thought process, I think it's helpful. Let me know if that's the case. But I think that, if you're watching this video, you may think that, I'm experienced or whatever, and I am good at a lot of problems, but sometimes I still struggle. And how I think through these problems, not even, there are a lot of times where I talk about how I think through these problems in the perfect case, and I get it right on the first try. But here's an example of something that I don't get right on the first try. And I'm like, okay, let's step back. Let's think about it, attack this problem. And here's how I use this thing where, notice that I never once think about it in terms of all these catchphrases with respect to like, oh, monostack or min stack or max stack or whatever. Even though I thought about it at some point, but what I focus on is more around the question that I'm trying to ask myself and to answer myself. And for here, I'm like, okay, here's the 5. I want to answer it such that like, okay, this is a suffix sum. And then for the suffix sum, I want the max suffix sum. And then I also want a way such that when I move from 5 to 6, now I have to look at one fewer numbers. Well, we want to use that thing to kind of build possible solutions, right? So that's how I would think about it. I think I talked about this a little bit, but now let's go over the complexity. The complexity, as you can see, well, this is O of n. We just look at each element once. This is O of n because we look at each element once again. We put in a stack, and the stack, we do a peek, and this stack is all O of 1. So for each element, we do O of 1 operations. And then now for the last part, we look at each element also once. We at most, even though I did it as a while loop, just for, I don't know why actually, to be honest, but this can only happen once because if this index is strictly smaller than this index, then it would have already popped up before as an invariant. So this is only O of 1, even though this is a while loop and it looks confusing. That's my fault. And this is obviously O of 1. So the entire algorithm is O of n, and it requires O of n space due to the stack. And that's pretty much it. This is a pretty cute problem. People have asked me a bit about this problem, but I haven't looked at it because I just never got to it. But definitely a good problem. I think it, and this is O of n time, O of n space is a good interview problem. It might come up in competitive programming in general. I would also say that even if you don't know monostack or even think about stuff with respect to the stack, like I kind of hint at, you could have used the priority queue, you could have used the set. Basically, the important part, the fundamental part, is to focus on the problem that you're trying to solve. And here, and I want to put, and I know that I've been saying that a few times because I really want to put emphasis on it, is that, for me, it's just about asking the type of prompt. And some of that is that we already analyzed this problem before. So it's not like we're bringing a vacuum. It's not me going, oh, yeah, obviously, it's just, you look at the first element, you look at this. And maybe some really good, smart practice people are able to do that. I'm not one of them. And, I'm not as practiced as I am on all these problems. So I go for but I looked at this algorithm, or we did an analysis and we're like, okay, these are the cases that we built on, even though we didn't mention it as much in the second half. But as a result, because of this, we separated into one special case, which we had some inkling about playing around with it in code, and then we imagined that edge case, which is a big edge case, but we imagined it in a way that formulates it in terms of what kind of problem we're trying to solve. And it turns out that we could use a monostack, but as I mentioned, we could have used a set, and it does change the complexity from O of n to n log n, but that's okay for a lot of things. And it's good. And also if that's the best you can do, that's also the best you can do, especially in an interview or competitive programming. In competitive programming, most of the time you would not care about the log n you would not care about the log n from the n log n. But that's all I have for this problem. Let me know what you think. This was a long problem or a long video for sure. But I hope that within that long video, it gave you, it showed you how I solve and work through this problem, a problem that I guess nowadays is probably a little bit harder medium, but it's still a problem that requires a couple of layers of thinking, as you saw. Cool. That's all I have for this problem. Thank you, and I will see y'all tomorrow. Bye-bye.